Archimedes. That's a name that sounds familiar to everyone.
Huh.
Fascinating with calculating areas of various shapes. His method was a method of exhaustion where he would just use smaller and smaller shapes whose areas could be calculated exactly to fill in an irregular shape. Right? As the shapes he used got smaller, then his approximation, right, the area he was calculating, got closer to the true area. We will build upon this. This is kind of the method that we're going to be using to approximate areas. Right, so in this process, areas bounded by curves, filled with rectangles, triangles, shapes with exact areas. We will be using rectangles. Right, so we calculate the area of each of these shapes, sum them up, and that is the area approximation. I said we're going to be using rectangles. Then the idea is, as we use increasingly smaller and smaller rectangles, the number of rectangles we have is going to get larger and larger, and the area is going to be a much better approximation. So notation first. Sigma notation is the notation used for sums. We use the Greek letter capital sigma to use or to express sums. So for instance, this is read sum from I equals 1 to n of a sub I. So that would be a1 plus a2 plus a3 plus a4, so on and so forth, till you get to plus an. Right? A sub I is the argument of the sum. It's the summand. The I is your index. The index is a dummy variable. We can use any letter for the index. I is just the most common one. Right, so the most commonly used indices, I, J, K, M, and N. So properties of summation. So we're going to have two sequences of terms, A and B. We're going to have some constant C. Sum from 1 to n of just that constant C, n times C. That is pretty easy to see, right? You add a constant to itself n times, it's just n times that constant. However, these are all properties that we will be using. So you can kind of think of this as sum algebra, the algebra of summations. So you may want to write these down somewhere and keep them handy. Second, this is the distributive property for summations. If you have the sum of C times A sub I, it's just C times the sum of A sub I. Again, that shouldn't be too difficult to see. Again, just distributive property. This one might be a little less obvious. You take the sum of AI plus BI, it's the sum of AI plus the sum of BI. I think the next one is, yeah. So I'll look at this one first. This is the associative property. Remember, associativity says that grouping doesn't matter, i.e. group doesn't matter. Combination of associative and distributive. Right? Again, if you have the sum of AI minus BI, it's just the sum of A minus the sum of B. This one's saying you can split summations or combine summations. Right? You have sum m between 1 and n. Well, then you can split your sum at m. Right? So you can go sum from 1 to m plus the sum from m plus 1 to n. And that also works in reverse. If you have two sums, and it's the same term, same indices. Let's say you go like 1 to 5 and then 6 to 20. You can write those as a single sum, 1 to 20. And so knowing these properties will be very useful. These next few sums are also going to be extremely useful. These sums will typically be proven in a elementary number theory or discrete math, depending on whenever you first look at elementary number theory. But now you're just going to take my word for it. First, if you just sum the first n integers, the first n positive integers, it's n times n plus 1 over 2. The sum of the first n squares, n times n plus 1 times 2n plus 1 all over 6. Yep.
I did remember it. And are we going to need to remember that?
Oh, yeah.
The one day where I don't want to take notes. Probably should have set that up. Is it 8 max or is it 4?
Hmm?
Isn't the bottom 4?
Mhm.
Okay.
That is the next one. The sum of the first n cubes, n squared times n plus 1 squared all over 4. That is as far as we will go in this course. But there are formulas for the first n quatrics.
Hypercubes.
Well, hypercubes is something completely different. I forgot to highlight the I and the I squared. So then, of course, you have the first n quintics, so on and so forth. There's formulas for all of them.
I think 4 would be quartic. Because that's what the polynomials are called. Quartics. 4.
It should be quatrix. Quatric.
Maybe it's
It may have 2 names. I've always just seen quatric. And then quintic, and then, what is it, sectic, and septic. 7, I don't like that one so much. So, nurse better hope I never go to the hospital and say I'm septic, because I will definitely make a bad math joke that way. Then you have the optics, the nomics, the decics, and I forget. There is naming conventions for everything above 10. I just can't be bothered to remember. Good, you've had enough time to write those down. What happened to that slide? No, did I? Why did it go away? That's better. Now we're going to get into a little bit of set theory. What we're going to be doing is creating what's known as partitions of an interval. Right, so a partition is simply a set of points which divide your interval. So you're going to have points x0, x1, x2, x3, x4, up to xn. x0 has to be your left endpoint, xn has to be your right endpoint, and then everything in between obviously has to satisfy left to right, x1 less than x2, less than x3, less than x4, so on and so forth. But notice what it doesn't say. It doesn't say that all those points have to be equidistant from each other. So for the interval 0 to 10, I could go 0, 1, 1.5, 8, 9, 9.2, 9.9, and 10. That's a partition. If they are all equidistant from each other, then the partition is called regular. For the most part, in this class, we will be dealing with regular partitions. Specifically, there are going to be 2 types of partitions that we're going to be using. Because again, notice this doesn't tell you how to pick your partition. We will be using left endpoints and right endpoints. what we do is first form a partition, a regular partition, where each subinterval has length delta x, which is b minus a over n. Okay, so the length of the interval divided by the number of subintervals you want. Of course, I don't have that delta x. Well, that's fine. What we want to do is then, from each sub-interval, we choose the left endpoint. That would be the left endpoint area approximation. No idea what's going on right now. Okay, something happened where all my slides are all messed up. The exception of they didn't define what delta x is, so let me write that on here for you. Plus you. So this is what we are doing, right? We have the curve, we form rectangles, where the height is determined by the left endpoint of each subinterval. And the length, or the width, is delta x. Well, if we have left endpoints, we must also have right endpoints. And where there's a left, there must also be a right. So your right endpoint approximation. And again, delta x is b minus a over n. The process is the same, except your height of the rectangle is determined by the right endpoint of each subinterval. And the idea is, as you increase the number of rectangles, so you're decreasing the sizes, it fits better and better. Right, so you're losing less and less area from the approximation. I think this is the left endpoint approximation, and this is a right endpoint approximation with the same idea. As you let the number of rectangles increase, the amount of extra area you're getting for this function is smaller and smaller. These are not the only ways to choose your sample points, right? There's also a midpoint that I'll say for Calc 2. I'll let you learn that in Calc 2. All right, but you could decide, oh, I'm going to do a quarter point or a 3/4 point. Or, I'm just going to pick a point at random in each interval. Doesn't matter. Collectively, these are known as Riemann sums. So you have a function on a closed interval AB. Let P be a regular partition, and I don't like that because it doesn't have to be regular. Be a regular partition of AB. Let delta x be the width of each subinterval. And for each I, let x sub I star be any point in that subinterval. In the subinterval xi minus 1 to xi. Then, any sum of that form is called a Riemann sum. I love Riemann sums. So I'm going to adjust this a little bit. I'm going to say that here, P is just any partition, does not actually have to be regular for the definition of a Riemann sum. We let C be your collection of sample points. Which represents just set C sub I. And we let F be the function, so don't really care. What we would typically do is write it this way. Riemann sum for the function with the given partition P and sample points C. Right, and delta xi is the length of that subinterval. Is a Riemann sum. Now, again, I'm going to reiterate that for this course, we will not be working with Riemann sums of irregular partitions. For the most part, they will be regular. I'm only introducing this to tell you or to indicate how integration is really going to be defined. And actually, the integration we study is just one type of integration. There is at least one more type of integration that I've studied, and that's a Lebesgue integral. If you think this sucks, look up Lebesgue integration on your own. What we find is if we let the number of subintervals increase, right? So we're letting the rectangle get smaller. That means the number of rectangles you have is getting larger. Well, that means the number of subintervals you have is getting larger. If you just let that go out to infinity, then wouldn't those infinite rectangles perfectly fill in the area? So the area is the limit of the Riemann sum. That is notation if your partition is regular. What is it if it's not regular? Oh, I'm so glad you asked. Why are you not confident? Thank you. Paste. Well, instead of letting n go to infinity, what we do is we say the norm of your partition goes to 0. The norm of the partition is just the length of your largest subinterval. So if you let the length of the largest subinterval go to 0, that necessitates the number of subintervals increasing to infinity. I wonder if we'll be seeing that again. Spoiler alert, we will. Next week. You guys are just so lucky because I'm one of the few who still teaches Riemann sums. Not many people teach the Riemann sum anymore. Which makes me sad. So calculate R sub 4 and L sub 4. 4x squared on the interval 0 to 2. Well, for either one, delta x will be the same. So the length of each interval is 1/2. The partition is that 0, 1/2, 1, 3/2, 2, which gives us the following subintervals. And remember, just check that your partition satisfies the 3 conditions. Is the first element of the partition the left endpoint of the interval? Is that A? Yes. The last element, is it your right endpoint? Yes, it's B. Now, all of your middles, are they in ascending order? There's a whole thing in ascending order. Yes, it is. This satisfies the requirements for a partition. That will be the same regardless of whether you're using right endpoint or left endpoint. The only way that changes is if you change the number of subintervals you want. So if I wanted R6 instead, that wouldn't be right endpoint. So delta x is 1/2. F of x sub I, and we may want to pay attention to this little bit. You will need that for when you code. Oh. But f of x is just x squared, right? I'm actually not going to have to worry about calculating x squared for each endpoint because we know the sum of I squared is. That was one of those forms. What's 1/2 squared?
1/4.
Times a half.
1/8.
I squared n times n plus 1 times 2n plus 1 all over 6.
180 divided by 6.
Technically 180 divided by 48. There's at least a 2. There's actually a 4. Be 45 over 12. Generally, though, since this is giving an approximation, we don't want exact. We want a decimal approximation because it's the whole point of this is approximating, right? So what is 45 over 12?
3.75. Wait, sorry, I can do that.
Gosh, I might.
Isn't it?
$3.75. Now you need approximations there. R4 is 3.75. L4. Was that, right? Isn't it just the same as that? Using index shift. That's the form I always use. Why? Because it's the same xi as with the right endpoint one. This one does have a disadvantage though. Remember those formulas that we looked at? What did the I start at for all of them?
At 1.
Can't use them for this. Here I start at 0. There is a workaround. And I'll show it. Well, actually, I don't need to do that, right? Using the same argument as before. We'll just get that, right? But here, we can't use the special formula because I starts at 0. But what we can do, when I is 0, what's the term? They're the same thing, aren't they? If I do the 0th term plus, then the sum from 1 to 3, I get the sum from 0 to 3. Now I can use that formula. We got lucky in this sense that it gave us 0. It won't always. N times n plus 1 times 2n plus 1 over 6. Oh, that's nice. 3 over 6 is 1/2. 4 times 7 is 28. 28 over 2. 14. What's 14 over 8? 7/4. And 7/4 is what, 1.75. So L4 is 1.75. Why is that 3.25? Did I screw something up? Did we mess something up here? No. Yes. No. No, 3.75. That actually simplifies down further to 15 quarters. I'm just going to assume that my notes are wrong. So it's 2.5. Maybe 7.5. No, half is, yeah, half is 7.5. 3.75. Okay, so my notes are just wrong. That calculation is off. Okay. We're good. So that's R4 and L4. But notice that was for a relatively simple function, wasn't it? Again, we're going to use a relatively simple function to find a formula for the Riemann sum, and then compute the total area, which means we're taking the limit. So I'm going to, we're going to verify that with geometry. So I'm going to note right now that I typically use capital N instead of little n. So if I default to capital N, that's why. So first we want delta x. Well, that's what? 3 minus 1 over our subintervals. 2 over n. I'm going to do this right now. X sub I. It is A plus I times delta x. It doesn't matter which endpoint you use. The Riemann sum, it's still the Riemann sum. And it can be shown that regardless of how you choose your sample points, the limit of all those sums is the same. It goes to the exact same area. So which method we use does not matter. The default method is right endpoint. That's what I'm going to be using. I'll let you do the left endpoint and show that when you take its limit, you get the exact same thing. R sub n, delta x, summation, I equals 1 n f of x sub I. Oh, but x sub I was that. And what's f of x?
What's here?
Now we do some algebra. Split this up. And I'm not going to write the indices anymore. It's understood I goes from 1 to n. So we can split it across the sum, right? But that 2 over n, in terms of the summation, that's constant, isn't it? That sum of 1, isn't it just n? Sum of I. Right? Distribute that 2 over n through. And those 2's are going to drop out. Oh. But really then, I can just write it this way. Right? There's the Riemann sum. Area is that limit, which is the limit, and then goes to infinity of 2 plus 2 times n plus 1 over n, right? What is the limit of 2? Hmm? So what is that limit? Just 2. What is the limit of 2 times n plus 1 over n as n goes to infinity?
Top is outgrowing the bottom.
Is it?
If you're adding one, then you have one.
So,
Is that part of that one?
what's the degree of the numerator? What's the degree of the denominator? That limits the ratio.
So it's just, it's,
Area is 4. Now let's do it using geometry. That's x, right? We went 1 to 3, didn't we? So the area we're looking for that area, right? I can make 2 ways to do this. First, that is what is that called, a rhombus? I think there's a formula for the area of a rhombus. I just don't remember what it is off the top of my head. So I'm going to do the easier method. That's a right triangle. What's the base?
40,
What's the height?
30,
There's a triangle. What's the base?
1,
What's the height?
1,
Isn't the area of our region the area of the larger triangle minus the area of the smaller triangle? Which is 4. Oh, then that must be 1/2 b squared minus a squared is the area of our rhombus. That matches our limit. So what this is saying is that that approximation method works. Or as I like to say, geometry was correct. Let me actually skip that for now. Come back to it if I have time. Table-based. Approximate total displacement of the particle over this interval using right and left endpoints. Well, how many intervals do we have?
That's it. Oh, fine.
5 of them.
Yeah.
There are 6 points, so the petition has 6 points, but that's 5. So that goes, right? Which means, in this case, it's going to be delta t. Point 5 is 5 halves. Delta t is 1 half. Oh, I guess we could just look and see that. I don't know. I'm going to keep with the decimals though. Left endpoint. This is also 5. There'll be the delta x times the sum of the values using left endpoints. Right, so it'll be v of 0 plus v of 0.5 plus v of 1 plus v of 1.5 plus v of 2.0. Right? Well, let's just take that sum. 6.1, 8.6, 9.8, 0.5 times 9.8. That's 4.9, isn't it? 4.9. Right endpoint, R5. 0.5 times. Now we're using the right endpoints, right? So we start at the 0.5. I'm going to work our way all the way over. That is 5.1, so that's what, 11.2? 12.3? Because that's 6.1. That would be 5.1, wouldn't it? 2.5 plus 2.6 is 5.1. 5.1 and 6.1? That's 11.2, right? And then 12.4.
Yep.
So it's half of 12.4. 6.2. Oh, but I missed something. What should the units be? Meters. compute R4 on this piecewise. So, how many subintervals do we have?
4.
What's delta x?
Zero should divide by 4, so 1.5.
Should be 1.5.
Just one out.
Should be 1.5. Let's list out. Let's call this R. The right endpoints. Right, so 0 wouldn't be your first right endpoint, right? It'd be 0.5. Then 1. Then 1.5. Then 2. And actually what I should do is this. So that's going to be my sample points. Let me call that R star. R4 would then equal 0.5 times f of 0.5 plus f of 1 plus f of 1.5 plus f of 2, right? So f of 0.5,
Is 1.5.
I'll go in here, right? 1 plus 0.5.
Yep.
F of 1.0,
42.
f of 1.5,
Would be 1.5.
f of 2.0, that's 3, 5, 6. R4 is 3. And again, I should be putting a 0.0. Right, so this 2 should have a 0.0, that 1 should have a 0.0, and that 6 should have a 0.0, whatever. Right? This one isn't going to be terrible because I'm going to use a calculator. Actually, I think what I'll do is I'll be nice. Not only will I'll do one of them on a calculator, and I'll show you how to use the sum command in Wolfram, because you're also going to need the sum command for your project. You go to code. Get generous. First off, number of subintervals, 6, right? What's delta x?
Pi divided by 6.
X sub I would be 0 plus pi over 6 times I, right? That should be L6, right? That sum. So it'd be sine of 0 plus sine of pi over 6 plus sine of 2 pi over 6 plus sine of 3 pi over 6 plus sine of 4 pi over 6 plus sine of 5 pi over 6, right? Oh, that's right, this asked me to do midpoint, but I'm not counting midpoint. So let's see, let me just write out R6 as well, so I have to come back. What am I using? And that would be R6, right? So the sum would be what? Sine of pi over 6 plus sine of 2 pi over 6, right then 3 pi over 6, 4 pi over 6, 5 pi over 6, and finally pi. So let's see how to do this. Both calculator and right, so pi is right there. Pi over 6. And I'll just put that in parentheses. Times. Sum. You want to remember the menu. Calculus. Sum. And notice it's going to lay it out nicely for you. Obviously, choose your dummy variable. I, we said it was going to be what, 0 to 5. Sine. So then trig is right there. And then just pick the right one, just sine. I'm again going to use parentheses to be safe. Pi over 6 times I. Oops, okay, so I don't need to go any further. I can just hit the tab, get out the sum now. Before I continue, what's the problem?
Oh, yeah, you're doing 0 and.
No, I'm doing the left endpoint for this one.
Oh, you're integrating.
Now I'm good. Now, I want you to see what this is going to give as it's typed out. That's actually not as hideous as I was expecting it to be. That's giving an exact answer. So if I just put a decimal after that 6, or I could also do it after the first 6, or after a pi, whatever. Just put a decimal somewhere. Now I get my approximation. There's the approximation. So let's say that is 1.9, let's just call it 1.95. Again, let me just put in parentheses pi over 6, right? Okay, so that's not that much of a big deal. Times, now it's a summation, right? Sum. What's the summand? What are we summing? Sine pi over 6 times, what do you want our W variable? We're going to stick with I, comma, braces. What's the dummy variable? What is its lower limit? What is its upper? That's the sum from 1 to 6, sine of pi over 6 times I. Now again, it's going to give me an exact value. So let me just I only want 2 decimal places. Okay, so you should remember the number 4 from when we did this method. Oh, wow. I wasn't expecting that. 1.95. I actually was not expecting that.
Oh, because it's
That's actually really cool. I got the same thing. Questions on Riemann sums and approximating areas?
So many. This is gonna take a while for me, I think. It's a little new.
isn't it
It's your
the,
first time working with sums, right?
Yeah.
the left-endpoint under does the curve? And the
Depends.
Or
Be careful, it depends.
depends on what variable, depends on the.
Is it increasing or decreasing?
Um,
Is it concave up or concave down? It depends on the function.
okay. Depending
But you could also get lucky enough with the curve that if I draw the rectangles, the amount that's under equals the amount that you go over.
that's like what's on the, or is it because it's a sine?
Yeah, I actually don't know what's going on. But yeah, it does depend on the curve on whether it's an under approximation or over, which one is which. For the most part, you're generally thinking about just strictly increasing functions, then yes, L is an under, R is generally an over. But it's only in that very special circumstance where it is monotonic increasing. Just gonna work through it for now.
I mean, what else am I gonna do? It's just gonna take time. Just a lot of practice, I think.
Don't forget to get stock tutor
Yeah.
or officer.
Yep.
And you're gonna need to know this because you're gonna need to know how it works in order to code it. So
Are you signing out today?
I don't think it goes up today. I think it goes up. I don't think it's up yet, right? It's up next week.
Okay.
So I give you a little bit of time. So I don't think I set it up to open up on the same week that the third project is due. Is the third project? Yeah, third project was due today. Or Tuesday, one of those.
Yeah, is it Tuesday?
Whatever it was, I didn't set it up so that you have no gap between projects. So I'm gonna give you at least one gap. Plus you have the test this week. So I'm like, I'm not gonna make you do a test and a project. So I'll let you absorb this a little bit, and then the project will be available next week.
Is there a review for the test?
He's gonna email me and remind me to look.
I didn't see one, but I don't know if you're.
It's possible I just didn't post it, so
Okay.
he's gonna message me and I'll look.
Don't worry.
Right, so don't forget about your third test. That is due Tuesday before class. That is just strictly the application of the derivative. Right, so that's Newton's method, but you don't have to do anything crazy with Newton's method. It just asks you like the first 3 iterations, I believe. I believe that's what it's doing. I don't think I said to 6 decimal places. I think it's just iterations, like the first few examples we did. The increasing, decreasing, concavity, extrema, related rates, optimization. L'Hopital's rule is in there as well. Right, so all chapter 4, basically. With the exception of one section in chapter 4, which is covered with this material. Oh, also, that was quite perfect timing. I did pass out the reference sheets last class, so if you didn't get one, just make sure you grab a copy before you leave.